getting back to where we were, same code. I'm going to now plug my servo back in. Remember, brown is aligned with ground. Another shortcut to usually remember is that servos have these exposed metal on one side of the plastic. And if the exposed metal is up as you're plugging it in, that's also the same. But ground to ground, brown to ground is always a good shortcut for knowing. Okay, so now I've plugged this back together. I'm going to go back to my code here. And let's take a look at this. So this time I'm going to change what the input is. And the input that I want to use is the sound level. So then I go up to the input and I scroll down. You can see one input. You can see that the inputs that we can use in the microbit are actually can be driven off of the sensors. It's not just a physical input. You can use the sensors as your input. And when you look at these blocks, you can see that light level can be an input. The compass heading can be an input. So there is a compass. When the microbit is flat, it can serve as a compass and know its ordinal heading. Temperature is an input. Acceleration is an input. Sound level is an input. And I'm going to click on the mores. Magnetic force is an input. I think magnetic force is driven off of the compass that's built in. So if you apply a different magnet, like you can use a magnet as a exterior trigger or sensor, and you can play with using that. One thing also, I've actually never played with magnetic force, but what I'll say is when you mouse over some of these blocks, you'll get a little more background about them. So for example, when I looked at that magnetic force, I saw those, I don't even know what that is, epsilon or whatever, something T, and those happen to be micro Teslas. And so didn't even know what a unit of measure of a micro Tesla is. But if you then click on, when it does that, let me see if I can do this. I think if I left click on it, I can get to help. And then it'll actually give me a more detailed information about this. This is helpful because often students will grab a variable or grab an input and not understand what the unit of measure is that it is using. And that can definitely affect their code, because if you're not sure how it's measuring something, you can't write your code around it. So it is using around the compass. It's along different forces, and it's measuring the magnetic strength in the X direction. So that's another thing to think about, not to get too digressed here, but if you are using a magnet, the Y is up and down here. And so if I'm trying to test something where the magnet is closer and further here, it may not sense much. And then the X, actually that's the Z, but if like the Y, it might not sense, and the X, it does sense. Actually, in this case, it's for the X direction. So you can actually pick which direction it's sensing in, and that's something to have in mind. If you're not sure what the directions are, if you go to the accelerometer page on the microbit, or if you just Google the microbit and look this up, you can see where the directions are. So let me just pull this up here. On the BBC web page, you'll see that flat is X is, as you're staring at the microbit, is left and right, Y is away and from you, and Z is up and down. This is particularly important for the accelerometer because the accelerometer, when the microbit is flat, is feeling only a force, the force of gravity, in the Z direction. So the X and the Y forces should be 0 on the accelerometer when the microbit is flat. This is another little detail to be on top of. But anyways, we're doing a little tour of these and what's going on here. All right, that's the magnetic force thing. Closing this. All right. So getting back to our code, what I wanted to do to make a chatbot is to have it react to sound. So if we go back to the inputs and I go scroll all the way down to the inputs within the microbit V2 specific ones. So if you have a V1, and once again, the difference between a V1 and a V2, the V1 has a straight bottom, the V2 has the ridges along the bottom. That's one big difference. So down here, there's a sound level. So let's just, for the sake of having fun, drop in a forever loop where the angle is set to the sound level. And let's see what happens when we do that and upload that program. So I'm going to plug in my microbit. And download the program. Okay. I'm not sure what all of you see, but let me see. I'm going to go to mine here. And here I am being completely silent. And there is some background noise here where I am. But you'll notice that this is just flying around even when it's silent. Now, when I am loud, it'll definitely move more. But there's a jiggle here when it's silent. Okay? And that's what's happening there. For one thing, we just took this servo level and set it directly to the sound level, right? And so if we look at sound level, let's actually click on there and click on help. So I right clicked on it and I'm selecting help. And my computer is incredibly slow today. This goes through the sound level. And so one thing you'll notice is it's going to give me a number between 0 and 255 for the sound level. And remember, the servo only went from 0 to 180. So really loud. So one thing that we notice right out of the box is the servo can only go to 180, and this is going up to 255. So right now, super loud sounds are going to go beyond the range of the servo. But also, even small sounds will probably, like small background sounds that it can sense, will make that motor work. So how can we get around doing that? I'm going to go to, for some reason, my go back thing is just not working. Let's try this. Okay, I guess I'll just click out of there. So one of the things that we can do here to change this is a slightly more advanced thing, but it's if we go into the math functions, we can map the sound level to a range that makes more sense for this servo. So it is just like a mathematical mapping of saying, I have something that goes from 0 to 255, but I only want it to go from, what I really want it to go is from, so let's say it goes from a high of 255, and I want to map that from 0 to 180. 180, not 280. All right. The other thing I might want to do is say, you know what? I want you to ignore everything below a certain sound level, because it's fluttering a lot when it's just sitting there quietly, because it's such a sensitive sound meter. Maybe it's going from 1 to 10 or 1 to 20 just because of the ambient noise. So I want only a loud noise to trigger it. So I'm going to just arbitrarily pick 40. And I'm going to say, I want the sound level, I want to map only from 40 to 255 against my servo. And what is that going to do? That is going to say, by doing this, mapping it above the bottom threshold, I've now let it basically ignore that small sound that was creating that flutter earlier. So let's see what happens here now and plug it in and download it. So once again, I went into the math blocks. I grabbed a map function, and then I dragged the sound level block into the sound level input is what I'm mapping. And so I'm taking whatever the sound level is, which if you remember from the help, the sound level was being measured from 0 to 255. So I know the max is 255, and I want to map it to my servo from 0 to 180 because that's the range of the servo. Okay. So now I'm going to go back to the screen here. And you see that now when I'm silent, it stops moving. Whereas before, it kept fluttering on me. And so that's a great way to say, okay, now I've gotten this set up so that the servo is moving every time there's sound, but it's not moving too much because I don't want to have it constantly jiggle with every ambient background noise out there. And depending on the background noise of where you are, you can change that low as high as you want to avoid that background noise. So we've gotten this part here working. So I'm going to turn this off. And now we're going to get to the fun part, which is let's make a robot that is going to be a chatbot. And this will be a good example of a lot of the troubleshooting we have to do in doing this. So I've got my box here, and I am going to take a part of my lid to make the mouth with it. And in this case, I'm going to use this as the front of the face here. And I'm going to try to, let's see, I'm going to make a mouth where the bottom teeth are fixed, but then the other teeth will pivot off of that mouth like this. Let me get this going here. And so I'm going to, this is sometimes, I'm going to just draw these teeth like this. Because I didn't grab scissors, I'm going to use my canary cutter. This might actually be easier with scissors, but so I'm going to glue this to the bottom here. And since earlier I was extolling the virtues of glue dots, I'm going to find my glue dots and use some right here. As I'm sure you folks all know, the secret to a glue dot is you peel it back. You do not try to touch that glue dot. You drop it onto where you want, rub it on, try to peel it back easily there while keeping it stuck to whatever you just did. And in this case, it's not doing a very good job of that. Oh. And let's try another one. I'm going to put this one here. Angle it off. I'm using something else to just hold that glue dot down as I pull it back. Oh, these glue dots are tough. And not always. If you have the confidence to use a hot glue gun in the classroom, those are also a quick solution. Tape would have been fine too, but okay, these glue dots are funky, but all right. So I am now going to put this, where's the glue? Over here. Okay, that's glued in there. Might as well color in the inside of the mouth. Okay, so now we're going to want to have this mouth spin up and down like this while it's talking. So I am going to want to connect my motor to this side over here. Okay, so I'm gonna put this here. Just to be safe, I am going to align my motor so that there's enough of an overhang over here to do that. And then take anything sharp. Here I've got this, I can use my little screwdriver as an awl, and I'm gonna punch here and here. And now I've got those two holes. Now you could either use your screws to fasten it down, push through and screw in on the other side. Just looking at this, one of the things I'll say that I am realizing I might have messed up on is that I put this really close to the edge here, which is great. It's going to give a lot of clearance, but it might be hard to reach. Yeah, you can see that from the inside here. I can't actually get this. If I was screwing this on, I can't actually get in there because I'm on the inside there. So I might put in a new hole just a little further in of this that I'm going to use. Okay. Like I said, screwdriver, screw them and tighten it down. I'm going to just use a pipe cleaner that I'm going to take on this side and over here on this side. One of the reasons I do using things like pipe cleaners and brass brads is when students realize that you can do these things with just about anything, it makes it a lot more accessible to them. It doesn't seem like this unattainable thing of where am I going to find a screw like that kind of thing. They can just build it themselves. Okay, so I've got my bottom teeth here, and I'm going to put my top teeth like that. And so to do that, I'm going to put some more glue dots up here. I don't know about you guys, but my glue dots, which I did spend the money, not on the supposedly cheap Chinese knockoffs, but glue dot branded glue dots, are giving me a hard time. But I'm going to put glue dots on this servo horn. And then connect that to my teeth. Oops. All right. So I think let's do it like this. And now I'm going to turn on and see what's going to happen when I do this. Okay, brace yourselves, folks. Lift up this a little higher, get a good view of what's going on. And let's see what happens. Turn this on. Okay, so this is interesting. So this is something. This is. All right, so silent. Whoops. I just got stuck there. Silent is straight up and down. Okay, that's a solvable problem. I'm going to just take this at silent and then move it like that. All right, so that now I have this. This is my monster teeth. And let's see what happens. Hello. That's not bad. It opens up just like I thought it would. Now, there's some making considerations here. As I look at this, there's some considerations. For one thing, it opens its mouth a lot. Whoa. And so maybe what I should do, I'm going to turn that back off, is go back to my code and say, you know what? It doesn't have to go from 0 to 180. What if I say from 0 to 90? If I make it open half as much, because it's supposed to look like it's talking and nobody fully opens their jaw like that. So let's just drop that down there. And this is some of the testing and iterating that is the kind of one of the powerful things of physical computing in general is you write your code. It doesn't work in the real world exactly like you wanted it to. And then you go back and you tweak your code to make it work better. And this super simple example is an example of that. So now I'm saying, instead of mapping from 0 to 180, I'm going to map from 0 to 90. And so I can go back and take a look, upload my program, download it. I do not know why the servo is just moving randomly when I plug in my thing and it does this. That's something I never fully understand. But okay, my program's been downloaded. All right, so I'm gonna get back to my, glue this guy back on here. And turn it on. Okay. That looks a little better. It's not as crazy as it was before, but even now, maybe 90 is too much anyway. Actually, I think I'm going to go back down to 45 and see if that looks more realistic as a talking thing. I'm going to my code. I'm going to change it to 45 and download that. One thing you'll notice is that when I did plug it in, my servo was moving away randomly. That could be a good time. That, you know, if your students are experiencing that, sometimes that'll break whatever they've made, and it's a good idea to maybe just disconnect the microbit and just program it in the microbit directly as opposed to otherwise. So now you'll see it doesn't open as much, but it looks more realistic. Now it looks like it's talking a little more like a talking thing than just I don't know, something just wildly opening up. But this is where the students can build their own things and try to decide. This is one of those opportunities where their design will drive their code. And they will fine-tune their code based on whatever they designed in their robot. Another thing, for example, that some students may choose to lever something. So if I instead of connecting it like this to the back of it, like to the side so that it turns straight up, maybe I want it to look more like a jaw that opens and closes. So then I might instead take this same code. Let me take this apart. One of the downsides of using a pipe cleaner is I don't remember which way I twisted this. Hold on. So for the canary cutters, I bought those directly from Canary Cutter, but you can get those online. But if you're interested, you can email me and I can figure out what I was paying for those, and I'm happy to sell them at cost plus shipping of the raw blades. But I buy these in bulk from Canary directly. So what I was talking about as well was this idea that what if we, instead of making it just a lever like that, we want to make it a jaw that opens and closes. Let's just do a quick project that way. And I'm going to cut off another piece of my box. think since this box is longer than it is wide, I'm thinking that maybe I could do something that kind of pivots like that. And let's see how that works. Okay. Give it some teeth. So it's going to pivot like this. So I'm going to have to put the motor popping out sideways in here. So in this case, I'm going to take this motor and figure out how to align it in this way. But let's have it like that. I will poke a hole through it from this side. Oops. Got it like that, but I'm going to put it on the inside, which means I need to open up a hole here. So I'm going to since it's the inside of a box, I've got to lift up those flaps there. It's a pretty sturdy box, but you can see my little hole in there. So now I'm going to take this and poke it through there and turn it on, stay quiet. If I turn it on and stay quiet, it finds the 0 point. So now I can connect this to the side there. And now I can maybe use another glue dot on here because my glue dots are getting a little worn out. Now you'll notice I haven't fastened my servo yet because this is a problem that you could have your students solve through code if they run into it. But you'll notice I could have put the servo in with the wire up or the wire flat. And the difference is it would move in a different direction each way. And I'm not sure which way it's going to move right now. And if it's going to move in the correct, so the difference is 90 up here or is 90 down here? And if 90 is up here, that's great because that's where I want it to go up and down like that. But if 90 is down there, I can either solve that through my code, I can mathematically reverse it, or I can just turn my motor around. And so if you are trying to get the students to troubleshoot something based on their code, maybe you want them to figure out how to mathematically change it. Now, as a quick solution, I'm going to put another hinge here, just poke it in here with and this will be, let's see what happens. This is what I get for, all right, so this isn't a super smooth hinge, so let's make that a bigger hole so that it's, all right. You see, now it opens up, so I got lucky. It opens in the right direction. So if I put the bottom teeth on again, where did my bottom teeth go? Now I have a robot that has a mouth that opens and closes like this. But I might have, if I put my servo in upside down, it would be opening in the wrong direction. And like I said, you could either choose to make that a problem they solve in their code, or you could have them they could choose to solve it mechanically. But 90 degrees to the motor is based on the side or direction it is. So that's the cardboard chatbot project, and you can see that there's a lot of ways to get here and to build it. It's a fun building project. If your kits only included 2 googly eyes, which I didn't want you to use today because they're for the other robot, but if you have a lot of googly eyes, you can put them on. Everything looks better with googly eyes. And yeah, that's the that's that project. And we are actually getting close to the end of today. I will send out some additional links and information about the canary cutters and whatnot. But before we wrap up today, any questions or any feedback on what we've got here so far? I'm going to take the silence as just everybody is in such awe that they don't know what to say. But the okay. So yeah, so I think that's it for today. As I said, even with these longer ones, it's always going to be 45 minutes plus a break and maybe some Q&A. I would really encourage everybody to try to build some of these yourself and try to run into problems. Try to see what happens. Where does it break? What are issues to think about? Areas that your students will run into are things, if they try to make too big of a mouth, you may stall out the servo motor. If there's too much of a lever arm, I don't know if any of you have ever done things like the robotic petting zoo, but sometimes if that servo is trying to lift too much, it can stall out. Today the constraint has been these glue dots can only hold on so firmly, but if you're using hot glue and really fastening to that servo arm, or if they're even 3D printing and designing something that connects there, they may find that things don't work because of that. The other thing is, in this example, for example, we could have hidden the microbit inside, and that might affect the sound sensor as well. And we might not have been able to see the sound sensor, and it may not work as well. So knowing the sensor is on the front of the board, it's that microphone. And so if the board is, the closer you are, the more dramatic the talking, and so it's good to know that.
Because I was trying to connect this to the motor and it wouldn't lift. So I found like a liner inside a hat. When you buy a hat, it has that thin liner.
Yeah.
And I tried that and it did it much easier as a side mouth.
Yeah.
Exactly but it worked much better. So yeah, the weight can really affect whether it's going to move or how much it moves.
Yeah. And that is if your students want to build one of these like this, it's good for you to know what issues they might run into. And like I said, the biggest ones I would say that they're going to run into is that range. Depending on the mechanism you use, you want to tweak the range that it moves based on sound level. You almost always want to do that lower range cutoff because otherwise you get this weird flutter constantly, which is annoying. But the upper range, you want that lower range cutoff on the first half, and then you want to map the upper range based on the mechanism that they are using. So, for example, if they are using a geared mechanism that increases, you might have a smaller range. But if you're doing a geared mechanism that decreases the load, so one way to handle torque is to add gears to it, is to decrease the load by gearing it up or down. That's obviously a more advanced student thing. But in that case, if it's a heavy thing that they're gearing the load down on, you might want it to go to 180 because a 180 spin might only move the final lever a certain amount because of the way they've geared it. And yes, I will figure out today a place to post these videos so that you can have them as a reference, and we will have that all like that. Any other questions before we sign off for the day? All right. This was fun. I hope you guys enjoy making a little more chatbot monsters. I think like I said, this is a very fun, engaging little project. And even though certain layers of it, like that math and the mapping, might sequentially be something you want to cover later in a coding class, it's not a bad thing to introduce them now if you want to give students an idea of what you can do, because then we can come back to things. But this is a really fun input-output project that explores making and coding, and that I like the projects that force you to go back and tweak your code as you do things. I think that for me, the whole purpose of physical computing is to encourage that feedback loop, that idea of I've designed something, I've tried it in the real world. Oh, that's not what I wanted. I'm going to go back, look at my code and change it. And that's encouraging students to do a project that does that is a good intro to that process. And I like this chatbot as one. Simple code, but there's a lot of tweaking you can do to it. All right, then I will see you folks next Tuesday, and I will send a follow-up email with links and videos. And look forward to seeing what you all make on your chatbot. Next week, we are going to continue the sequence of the class, which is starting to explore functions, loops, and then logic and loops, and explore how loops are used and designed in MakeCode, because the forever block is basically a continuous loop, whereas the loop blocks are more controlled loops, and we'll talk about the difference of those and how that works in your code and how you want to think about them when you do use them in your code. And yeah, I mean, I think next week is going to be another one of more explaining components and things, but we're slowly inching towards more of a design thinking project of a very useful monster. So I do encourage people to start thinking on the back of your heads of what kind of very useful monster you might want to build yourselves. And we'll see where that goes. So thanks you, everyone, and I look forward to seeing you next Tuesday.